Morning. Come on in. Yeah. Okay, so as I was just saying, today we're going to do a little bit more pattern information because we didn't have time to do all of these things last time because of the holiday, and then I'm going to switch to seminar mode, as it were, and talk from my laptop. And I sent out a homework 3. Don't worry, it's not for credit. Okay, it's just for fun. Which for those of you who want to learn about pattern formation techniques, you can learn about that from that. So it's kind of fun. Okay, so what we did last time, we talked about linear instabilities and pattern formation. And what I want to do now is I want to talk about how one derives a long wavelength description of these sorts of problems. So one of the main things about this course has been that we look at physical systems, we coarse grain them, we look at their large scale properties, and we want to know what are the techniques we can use to create such a description. And we've talked about that in near phase transitions, we've talked about that well below a transition to an emergent state, and now I want to talk about it for pattern formation. So what I'm going to tell you now is in section 7.6 of my Emergent States of Matter lecture notes. And what I'm going to show you is a very quick and dirty way to derive equations that describe the long wavelength behavior of dynamical systems. But the correct way to do these things is using the normalization group. But we're going to do it in a quick and dirty way. And in the homework, the optional homework thing, well, the for fun homework to make your holidays more exciting, make the summer holiday more exciting. You'll work through this method I'm going to show you right now and actually try to derive something that was not known until it was derived by the normalization group. And it wasn't derived by me. It should have been derived by me, but I was too lazy. So I'll explain that when we get to it. Okay, so here's the question. How do we study patterns near a bifurcation at long wavelengths beyond the linear regime? So that's the question that we want to know the answer to. And why do we say beyond near a bifurcation? Well, just like phase transition physics, everything that we talked about last quarter was all about what happens in the vicinity of the critical point. So you might say, is there anything that happens in the vicinity of a bifurcation point? And the answer is yes, there is, and this is what we're going to derive. So I'm going to start off by talking about a one-dimensional, zero-dimensional dynamical system. So it literally has some variable which are called u, and it has a time equation of motion. U dot equals f of u and epsilon. So epsilon is a control parameter, and u is some variable. Okay, so what is the basic idea? So the basic idea is to kind of copy the Landau theory idea. And so what we're going to do is we're going to say, let's expand f of u and epsilon near the critical point epsilon c, where a pattern first forms. So what we're going to do is we're going to say, all right, so f of u is some constant plus b times u plus c times u squared plus d times u cubed plus dot dot dot. So that's just an expansion, and the idea is, well, what we want is that u equals 0 is a solution of u dot equals 0. Why do we want that? Well, we expect there to be a steady state where the system has no pattern at all, and that means that u is just a constant. So we'll say that constant is equal to 0. So if we need that, then that tells us that the constant a must be equal to 0. So that's the first thing. Now the next thing, so this is the first criterion. Second criterion is that we expect that near epsilon c a pattern forms or something forms.
Wouldn't that tell you that B is 0?
No, no, it doesn't. We're going to get to B and so on in a moment. But for the moment, I want U dot equals 0 when U is equal to 0.
So like U dot would be B plus 2CU plus.
No. U dot is F. Okay, right. So now what we want to do is we want a pattern to form near epsilon C. Specifically, we want B to change sign at epsilon equals epsilon C. So for that to happen, I'm going to say that therefore B is equal to some B naught times epsilon minus epsilon C plus something of order epsilon minus epsilon C squared. And we're not going to deal with that. And I'm going to specify that B naught is a constant that is greater than 0. So that's going to be the first thing. So that's going to guarantee that the B will change sign. And then let's suppose we have symmetry. So let's suppose there is a symmetry requirement. So we're going to suppose that there is a U goes to minus U symmetry in the original equation. So that means that then the coefficient C should be equal to 0. And so what that tells us then is that if we put all these things together, the generic equation should be of the form U dot equals RU plus DU cubed, where this coefficient R is equal to B naught epsilon minus epsilon C. And D, we haven't specified whether it's positive or negative at this point. Okay, so now let's so now we've got that. Let's take a look at what are the possible steady states. So what we may have is, let's suppose first of all that D is indeed negative. Then we could have a U is equal to 0 when R is negative, and then if R is positive, then U can be 0, but you can also have a solution that looks like R over D to the 1/2, and this is where I think there is a well, I think there's a typo in these notes, so I think this should be minus D. And if I had the case where D is positive, then I would get U is equal to 0, R is less than 0, and U is equal to 0 plus or minus R over D to the 1/2 when D is positive. No, I don't agree. No, I got this wrong. No, what I wrote here was wrong. Okay, and what I have in my notes is correct. Okay, so let me just change this. All right. Nope, that still doesn't make any sense. This one, something's wrong here. Wait. Okay, so this is a solution. R is positive. So I need D greater than 0. So here D is negative. So why is this such a mess?
Because if R is less than 0, then
So this should be R is great. This one here is R is greater than 0. So if R is greater than 0, then I need, then the solution is always minus D. So, and D is negative, so this is plus or minus R over minus D to the 1/2. If D is greater than 0, then I need the solution to be the other way around. R has to be greater than 0. R has to be negative. So this is R greater than 0 and R negative. So it's something like that. Okay, whatever. I think what I wrote there is right. So you want to check this, because obviously there's a typo. Okay, so anyway, what's important is what the graph looks like. So here is my control parameter R, here is U, and these are two different cases. So in this particular case, yeah, I didn't explain this very well. Let's just look at this case though. So this is the case.
that should D less than 0 on the left, right?
Yeah, exactly. No. Yes, D less than 0. Exactly. This is the case D is less than 0. This is the case D greater than 0. When D is greater than 0, I have to have another term in the equation. This is the thing I didn't tell you about. So I need another term here, EU to the 4th. So let me draw for you what it looks like, and I'm not going to spend a huge amount of time going into this. Okay, so this case is called a supercritical bifurcation. And this one has got a finite jump, as you can see, and this is called a subcritical bifurcation. So I need to have a form that has this double from here. Here there is bistability. I'm not going to talk. I'm not going to spend much time talking about this, but it's super important case. But for now, let's just talk about this one. Why is this one important? This one here looks like a second order phase transition. The U looks like the order parameter, and you can see that U grows slowly from 0 when R becomes positive. So this is the case that we're going to be interested in. So U tends to 0 as R tends to 0, and this is just like the magnetization tending to 0 as T tends to TC from below in a phase transition. Okay, so that's the picture, and you can see explicitly that if I look over here on the left-hand side, this range over here, this thing over here, was what we called linear stability analysis. And that's what we talked about last time. And then we talked last time about how exponential growth, you can see here if R is positive, then U is going to grow exponentially. And then if D is negative here, it will then cut off this exponential growth at some finite value. And that's what we calculated over here on the left. So D is less than 0, and this thing will asymptote out to this value here. So this thing over here is what we talked about last time, which is the idea that the nonlinearity stabilizes the pattern. Nonlinearity stabilizes. And we saw this in Landau theory, and now we're seeing it over here as well. Okay, so what we want to focus on now is this regime over here, and we're going to try to find a long wavelength description of this. So what is our goal now? So we're going to look in this regime, examine the vicinity of the supercritical bifurcation. So let's see how we go about doing that. So what is our basic idea? Well, we're going to the next thing we're going to do is we're going to add space. So now we're going to say, well, everything is the same, but now what we called U as a function of T and epsilon is now going to be an infinite number of variables. So U of X and T and epsilon. And so we can think of this, say we're looking at the velocity field in convection, like we talked about last week, or it could be a temperature or something like that. So that's what we're going to look at. And then we saw last time that we can have ordering, say, along the space direction. E.g. roll patterns. So we're going to be thinking about it looking like this. This is the x-axis, and then I'm going to be plotting along here, say the maximum of these rolls. So they're like this. And if I were to plot the actual function, what it would look like is, what is it doing? Stop. Something like that. So there's some pattern. So that's the picture that we have in mind. So the next thing we might ask is, well, this forms a pattern. We've spontaneously broken translational symmetry to this pattern, this symmetry here. So you might ask, well, are there Goldstone modes in this kind of problem, because we've broken a continuous symmetry? So there are Goldstone modes. So all of that carries through, and let me show you that. So suppose, for example, I said, well, this is all very well and good, but actually I'm now going to change my origin. Okay, so this thing over here is the solution shifted by, say, some amount x naught. Okay, so let me show you how that's described in this kind of system. So we could describe this u, the u variable, we could describe the pattern as proportional to a e to the I some wave number q, and then its complex conjugate. So that would be a way to describe it. So this would be a, this would be the lambda, and lambda is 2 pi over the wave number q. So that would be how we describe the system. So think about it like this. Suppose I make a shift in x. So x goes to x plus x naught, let's say. Then u goes to a e to the I q. This one is q dot x, and there's going to be plus I q dot x naught, and this thing over here is equal to a e to the I q dot x plus some phase shift. So the translational symmetry in this description of this kind of periodic density wave, it turns out to be the phase symmetry, the global phase invariance of this description of the system. So the global phase invariance is the equivalent of Galilean invariance. So what does that mean? Well, let's suppose now we say, well, we want to have an equation as an equation for this amplitude A. So this is what we want. So we've got here some amplitude A. We've pretended right now that it's just a constant, but actually what we expect is that A is actually some function itself of x and t, but this has a very slow variation in space. Compared to lambda. So we've got a variation in space. There's a scale here, which is this wavelength, but there can also be a scale of variation of the amplitude. So let's just have a look and see what that would look like. So I would see something like this. Something like that. And then this scale here is 2 pi over q, which is the scale lambda. And then if I want to write what is the amplitude, well, the amplitude is this envelope that I'm drawing like this. So that's the amplitude. So we want to know what is the equation for the amplitude. So it's going to satisfy a partial differential equation, and now the question is which one. So I'm going to show you how to derive that. And you can see that this is a problem with scale separation. When we talked about critical phenomena in the first quarter of 2024, we had the lattice spacing, which was on the small scale, say a magnet, and then we had the long wavelength, which was the correlation length that described the large scale ordering of the system. So you can think of this lambda as being the analog of the lattice spacing. This is the small length scale, and this amplitude is slowly varying. So that's like the correlation. Okay, so let's try to construct this equation. So we're going to do a quick and dirty and the right way to do this is by renormalization. But there's a lot of math you'd need to do to do that. Of course, I'm not going to do that. So I'm going to do it in the following way. So step one. Let's use symmetry and analyticity. So I know the equation has to be something like this. It's going to be dA by dt equals something. So it's going to certainly involve something to do with the equation for u. So the equation for u, where is it over here? U has to be positive in order for there to be a pattern at all. So what we expect is that the amplitude is going to be proportional to, there's going to be a term that looks like that. So there's going to be a term that is linear, but then there's going to be a term that is nonlinear. And how does that term going to look? Well, it has to be invariant under phase rotations. So if it's invariant under phase rotations, then it has to have the form a times the absolute value of a squared, okay, plus higher orders. So in other words, if we know how u behaves, so u behaves like this, that we have on the left-hand side, then A, you would expect it to look like that, but it has to have this phase invariance in there. So it has to be invariant under phase rotations. Okay, so are we done yet? No, we're not done yet, because we haven't got any space in this. So this is step one. So now step two is we need to add space. Now this part is very subtle and is very it's a very clever argument. You may not get it all the first exposure. So what we're going to ask, so here's the strategy is this. This is a very dirty trick. The strategy is we're going to construct the spatial structure by looking at the dispersion relation of waves. So actually what we're going to do is we're going to go backwards. We're going to do the derivation. We're going to do something which is analogous to the way that Schrödinger derived the Schrödinger equation. Okay, so what we're going to do is we're going to write down a dispersion relation, and then we're going to say, we're going to make a kind of quantization condition which relates frequency and wave number to spatial and temporal derivatives. So let me show you how we do this. So what do we expect the dispersion relation to look like? So we're going to look at the dispersion relation for about the uniform state of perturbations. So in other words, waves. So if I look at a Fourier component of a wave, let's just think what it must look like. So we're going to look at it at at a perturbation to the original equation, it's going to go like e to the omega t. So this omega is going to be an omega as a function of wave number q. So what is it going to look like? So let's just have a look then at what the dispersion relation is, just to remind you of something that we plotted last time. So last time we talked about instabilities, and we had this picture over here. And we said, well, if epsilon is less than epsilon c, we have something like this. If epsilon is slightly greater than epsilon c, it looks like that. And if epsilon equals epsilon c, it's going to look something like this. So that's what the dispersion relation looks like if I have a band of unstable wave numbers. So we can then ask, well, what is the shape of this? So this has the shape of a parabola. So that means that we can say that omega looks like this. It's equal to some constant, and then it goes like minus. If this is the value QC, so it's going to go as minus something like Q minus QC squared with some number in here, and then higher order terms. So that's what the dispersion relation must look like near threshold. The linear dispersion relation, as we saw last time, has to look something like this. So now let's put in the coefficients. So specifically, I'm going to say that omega, we want this equation to be dimensionally consistent. So it's going to go like this. So there's going to be a tau omega of q. So tau is a time, omega is an inverse time, so that's dimensionless. Then we have r. So that r is our control parameter. It's a dimensionless parameter. And then I've got something that goes like q minus qc squared. But q has dimensions of inverse length. So therefore there must be a length in here. So I'll call that length scale psi. And so there's a length scale psi that goes in here. And then there's higher order terms, which go like q cubed and so on and so forth. Okay, so this must be, so this is generically the form of the dispersion relation near epsilon just greater than the threshold. Okay, any questions about this?
Is there any reason why two modes can at the same time be growing near the omega c?
Well, let's just do the simplest case first. Okay, so the simplest case is one mode goes unstable. Okay, this is hard enough. Okay, so there's any question you care to ask, you can construct a situation where it does that. Okay, so this is the easy part. Okay, now I'm going to show you the clever part. So the clever part of this argument is to say, okay, so this is great. So now what we're going to do is the next step. So this is step 3. What I'm going to do is I'm going to modulate this state by the amplitude I'm going to write it like A times e to the I qx x plus I qy y. Okay? So let's just be crystal clear what I mean by this. So what's going to happen is that q was initially the vector qc and 0. Okay, we're talking about these waves going along in the x direction. So we have a wave number about qc and nothing in the y direction. So that's what we have. But now what we're going to do is we're going to modulate it. So then the function is going to have a wave number which looks like this: QC plus QX, QY. Okay, so I start off with a state like this, then I modulate it by an amount with a different wave vector, QX and QY. Just like we had last time, there's two different wave vectors. There's the wave vector of the pattern, which you can't control, it's just what the system does. And then there's the wave vector that you control by perturbing the system like this. So let me just write that down so it's crystal clear. So this one is what you control, as it were, in this argument. And then this one here is emergent from the system, emergent from the underlying PDE. Remember, I haven't written down for you the equation yet. The equation could be the Rayleigh-Bernard convection equations that we wrote down last week. It could be something more complicated. It could be from magnetohydrodynamics or anything like that. But the beauty of this argument is I don't have to say anything about where that comes from. Okay, so that's what it looks like. So now let's plug that into my formula over here. So let me put this formula. This is an important formula. Let me put this in a box. Okay, so now let's plug into here. So then what I'm going to get is that tau omega of Q is equal to R minus psi squared times the square root of QX plus QX squared plus QY squared minus QC minus QC, well, all squared. So that's what's up here. So magnitude of Q is just the square root of those things I wrote down, and so therefore I can say that this is equal to R minus psi squared into QY squared over 2 QC plus QX all squared. So now let's go and look at what the actual function looks like. So now our solution of the partial differential equation describing the pattern formation must be this. It's going to be u of x and y and t is equal to a of x, y, and t e to the I qc of x plus complex conjugate. And now let's plug in this formula. So that equals some a naught e to the omega of q and t e to the I qx x plus I qy y plus complex conjugate. So that's what the solution looks like. So I've started off with some PDE. I didn't even need to tell you what it was. What I needed to tell you was that it had a pattern forming on stability, and so the dispersion relation about the uniform state in the air threshold looked like that. So if that's the case, then we derive what the dispersion relation must look like, and then when we apply a modulation of the amplitude, so the amplitude itself is now going like this. So that absolute value of A is what I've called A naught. Over here, then the whole thing looks like e to the omega t. It's growing exponentially, and then there's this part over here. Okay, so now we're going to do Schrodinger's trick. Okay, so Schrodinger's trick was to say, okay, fine. So what we know is that omega of q, I have an e to the omega q, and that's the same thing as differentiating with respect to time. And similarly, if I were to differentiate with respect to x, then that would give you a qx, but with a factor of I, and a factor of qy comes from I d by dy. So therefore, what this tells you then is that from the dispersion relation, so from this dispersion relation over here, so while I've got tau omega of q, tau omega of q, that's now tau d by dt. And over here, well, I have qy, I now have dy squared, and so on and so forth. So I'm taking the dispersion relation and turning the formula for that into a partial differential equation. So what I get then is an amazing result. So then I get that tau dA by dt is equal to Ra plus psi squared d by dx minus I over 2qc dy squared A. And so this is the dispersion relation which describes the linear behavior of the amplitude of this system near R is equal to 0. This is linear, okay? This is just the dispersion relation, okay? So this isn't the answer to the question, okay? So we know it's not the answer to the question because we know that the pattern is stabilized by nonlinearities. So let's just look at what we've got. We've got a linear equation, but it does involve space and time. So that's good. And then we have a nonlinear equation back over here. We have a nonlinear equation, which is a zero-dimensional. But it is nonlinear. So we have those things. And the thing we want is a nonlinear equation which is space-time, which has space-time structure. And so what we're going to do is we're going to add these two parts together. Okay, and when we add those two parts together, we're going to see straight away that there's something that is in common to both these parts. So if you look over here, this is the equation over here, which has which just has no space. I'm looking at pointing to this equation. So this is the part that is linear. This is the nonlinearity. So this term RA is in both equations. So there's a term that looks like this. That's in the nonlinear term. If I go to the dispersion relation equation, that also has this term. So what that tells you is that the full final equations which is not double counting, is then tau d by dt of the amplitude is equal to r a plus d a absolute value of a squared plus psi squared dx minus I over 2 qc dy squared a. And that's our final equation. So this equation is now nonlinear and it has space-time, and this is anisotropic. Why it's anisotropic? Well, because we are looking at small perturbations about our waves that are going in the x direction, and that's the y direction. So it's clearly what happens in the y direction, what happens in the x direction should clearly be different. And we see that here in the way that this equation is structured. There's a term I missed. There's a term I missed. So this is dx squared in the x direction and dy to the fourth in the y direction. Okay. Can anybody guess why there's a dy to the fourth in the y direction? Could you have guessed that? Well, you could have guessed it. You could have done. Anybody here was an engineer? No? You weren't an engineer. No? Okay, right. Well, if you were an engineer, you would know that if I take if I ask what is the equation for a beam and I bend it, that equation is d4 y by dx to the fourth plus y is equal to 0. Okay. In other words, the bending beam obeys a fourth order differential equation. Okay. Why? Because it's the curvature. It has energy. When you bend a beam, you're inducing curvature. The curvature is d2y by dx squared over some first derivatives squared. And so when I take it, so the energy of a beam shouldn't depend upon which way I bend it. So it's got to be like proportional to the curvature squared. So it's going to be a fourth derivative of the displacement. So engineers know that, and you can derive it in a much more, textbook way than the way I just told you it. But that's the quick and dirty way to do it. And so you would expect it to be d4 in the y direction, and then in the x direction, you think things are going to diffuse, and there's going to be some cross terms. So this is this equation, and this equation was first derived by singular perturbation theory and asymptotic methods. This is called the Newell Whitehead equation. Okay, so this is where, so then now I'm going to tell you a story. Okay, so here's a story. So back in the middle 1990s, I showed you in the last quarter's course how you can use a normalization group to compute critical exponents in partial differential equations. So you can apply a normalization group to differential equations. I showed you that, like at the last lecture of the class, I showed you how to do that. What I didn't show you was that what we did for the next nearly 10 years was develop all these renormalization group methods to study asymptotic analysis for singularly perturbed differential equations of all sorts. And we used it to solve problems in fluid mechanics, low Reynolds number fluid flow, things like this. Okay, if you're interested, read my Reviews on Modern Physics paper in 2007. Okay, so we figured out how to derive everything that I just did today with a quick and dirty method. You can derive it systematically using methods that applied mathematicians developed called multiple scales analysis, which is what these guys use. And those methods require huge amount of guesswork to make work. And I wanted a method that was so powerful that even dumb physicists could just crank the handle and get the correct answer. Okay, you didn't have to spend 8 years doing a PhD in applied mathematics at Caltech in order to be able to do these very, very difficult calculations. Okay, so we invented that. Okay, and it worked. And what we discovered was that when you write down these perturbation theory equations, you get a whole bunch of divergences, just like the ones you get in quantum electrodynamics. and you use your normalization to get rid of them, and then you use your normalization group to fix those. And we talked about that a little bit at the end of last quarter. Okay, so when you do this equation, turns out, so say for the Swift-Hohenberg equation, a simple nonlinear PDE, which forms patterns, it's in the homework. It turns out that there are 8 divergences in the theory. They all have to be renormalized. So me being very lazy, I just said, well, let's just find the most divergent one, and let's just deal with that and forget about the others, because they're going to be subdominant in the asymptotic expansion. So when you do that, you get this equation. So great. Okay, the easiest physical review letter we ever published. The referee's report was just, yes, publish this, yes. Okay, but it was wrong. Okay, well, it wasn't wrong. It was right. So then Graham got the easiest physical review letter that he ever published, because he read my paper and said, these guys are idiots. There's 8 divergences here. I wonder what happens if you renormalize all of them. And he liked doing lots of applied math. He's a very famous applied mathematician and so on. So he went and did the whole thing. And when you do that, you get another equation. So when you do this, so this equation is not rotationally covariant. Okay, by design. But in principle, I should be able to write down an equation that for any pattern forming process doesn't distinguish between X and Y. So question, is there a rotationally covariant equation that does not single out X and Y specifically? So there is. So here it is. Go away. No. Try again. Okay, so there it is. So if you do this calculation properly, you get this. This object here, this square thing squared, is this operator. And this operator you can show is rotationally covariant. So this describes a system without any, you don't have to say, oh, there's rolls in the Y direction, I'm looking at variations in the X direction. You could just say, here's a system, it goes unstable, and what do you get? And so this is what you get. So this is from Graham's
even though that explicitly includes a unit vector in the X direction.
It's still rotationally covariant. Okay. So you can derive it over down. Okay, so it's not that trivial. And this equation had been guessed by Ganaratne and Swinney, but nobody knew where it came from. And so anyway, all right. So that's the story. So the story so far, we used a Landau style theory to describe patterns near threshold. And it's very generic, okay? So it also gives you scaling rules. So let me just briefly tell you about those. So this equation, I'm just going to use the Neural-Whitehead equation. So this equation has got dimension-4 parameters in it. Well, it's got all these length scales and things like this. So let's non-dimensionalize it. So what we're going to do is we're going to non-dimensionalize. So what I'm going to do is I'm going to define a new space scale. X is the square root of R over Xi times x. And we're going to define capital Y is equal to r to the 1/4 over xi over qc to the 1/2 times y. I'm going to define a timescale t is r over tau times t. And I'm going to define some new field psi, which is r over d to the -1/2 times a. Okay, so all of these are definitions. Okay, so the goal is to non-dimensionalize. And then if I take those equations, then my governing equation becomes this. D psi by dt is psi minus psi, absolute value of psi squared, plus dx minus I over 2 dy squared times psi. So you've got a single equation with no adjustable parameters that describes the pattern formation. And what it tells you is that it has experimental implications. So this, for example, implies that if I have spatial variations transverse to the roll direction, they will relax on a time scale which is order unity in my coordinates of x. Sorry, not time scale. Why did I say time scale? Length scale. Because there's no other length scale in the problem. Everything is now, there's an x. So the characteristic length scale is order 1 in terms of x. And so that will be, so that means that will be, this time scale will go as order psi over r to the 1/2 in physical units. You can see that this is going to diverge. If I look at spatial variations along the rolls, they're going to go in the y direction, so they'll have a time scale. So they'll have a, I don't know why I'm saying time scale. So let's just call this let's call this Lx. Let me call this Ly. So that's going to go like order psi to the 1/2 over qc to the 1/2 r to the 1/4. Okay, again, that's in the physical units, and these scales diverge as I approach the bifurcation point from above. R goes to 0. The order parameter A itself goes like r to the 1/2, just as we found in critical phenomena, and so we get these almost critical like scalings. These are mean field scalings and near the bifurcation point. So you can look at what happens when you have thermal fluctuations. They're very, very hard to observe. Excuse me. Those thermal fluctuations can cause there to be anomalous scalings at the onset of things like convection. Okay. So that's oh, I didn't say what the time scale was. I meant to say timescale. I kept missing that somehow. Timescale of the order parameter so that's going to be order this timescale tau divided by r. So again, the timescale diverges as a linear power of the small parameter. Okay, so that's how we can apply critical phenomenon thinking to patterns. All right, so now I'm going to switch. I want to show you some patterns.
Question.
Well, okay.
While you change things up, maybe. You brought up anomalous scaling.
Yeah.
So here we have this ratio of epsilon to QC. Can I think about this like how in when we were doing like the critical properties in the Ising magnet, we said that the correlation length divided by the lattice spacing, we're sort of taking that to infinity, but that ratio still shows up, and that's why we get the anomalous dimensions. Is that kind of the same thing happening here, where you have C is like the length scale of the pattern, and QC is like the wavelength of the original perturbations, and we're saying that that ratio should go to infinity, but it still shows up in the equations.
What is the cause of the anomalous dimension in this case?
Yeah.
Yes.
Or I guess even simpler, is this the same ratio of length scales that causes the anomalous scaling that we saw in like the Ising model?
It does have the same information.
I see.
Okay, so I'm going to unshare my screen, this thing. Stopping the sharing. Okay, now what I want to do. And I will just share the screen. What are the chances that this is going to actually work? Go away. Okay. All right, so let me show you. Okay. Can you see that, Lingwan?
Yes, I can see that.
You can see my desktop now, my
Yes, I
web
can.
browser.
Yeah, I
Great,
can see that.
brilliant. All right, so this is a website. I've sent you in the homework, the quote homework, the optional homework about this website. So it's a website where you can simulate partial differential equations. So let me show you. Of course, I probably have to reload it or something. Okay. All right, so there's a starting thing, and so you can vary the parameters in this differential equation. So this equation here, that is the Swift-Hornberg equation with the parameters that I've shown you. So this R is the R. This one should be set equal to 0 for now. This B is equal to -1 and set C equal to 0. So this is solving the differential equation that that we talked about. Let me show you how this thing works. It's a kind of cool website. So you kind of just do this. There you are, and then you can just watch the pattern evolve. Okay. So in the homework exercise I gave you, I asked you to think about the symmetry of this. So you can see that this thing is evolving into roles. So think of red as being fluid going up, think of blue as fluid going down. This equation, the Swift-Hohenberg equation, is a very simple version of the equations, and it's written in the homework. Okay, so you can see that these are roles. All right, so let me show you this. This number A, I told you to set equal to 0. You can see why. Now look at this equation. So V is just del squared of U. If you look at this equation, you'll see that with A equal to 0, this equation has U goes to minus U symmetry. Okay? I'm going to break that symmetry by making A go to a different value. So let's put it up like that. It's still evolving, but now look what happened. It now forms spots, and you'll see that they're going to form hexagons. I presume they're hexagons. Yep, forming hexagons as opposed to the roles. So the patterns you get depend on the symmetry of these equations. So anyway, you can do this yourself. You can look at the homework I sent you. Play with the website. It's very cool. Well, of course, what you should do is just write your own Python codes. So, all right. Any questions? Any questions about this? About this pattern formation stuff? Okay. So, all right. So let's let me turn this thing off. All right. And now let's make that go away, and let's do this. Okay, so this is today, and then next time I'm going to talk about more patterns, stochastic patterns in biology, and and again, this is just really for fun. So so here's the work. There's work on evolution, stochastic patterns, stochastic Turing patterns, and then the visual cortex, and then experiments we did on biofilms. Okay, so these instabilities that I've shown you so far, therefore equations which have got diffusion, so they're diffusion equations, and they have reactions. And if you look at the equation that I showed you before, the Swift-Hohenberg equation, you'll see that it had fourth order derivatives. Okay, so you can only get patterns if the dispersion relation has a shape like this. Hello, I'll see you again. All right. All right. So if you just have a diffusion equation, you won't be able to get a pattern because the dispersion relation will just have one minimum at the origin. So to have a minimum at a non-zero value, you need to have a form like that, and so you need to have a quartic terms. That can happen either by having fourth derivatives, or you can have two coupled fields that both diffuse and have reactions between them. So the person who figured that out first was Alan Turing, the famous mathematician and computer scientist in the 1950s. So he thought he had understood why leopards have spots and zebras have stripes and things like that. Turned out it's completely wrong. But nevertheless, it started this whole field of morphogenesis in biology and the idea of pattern formation in general, which then had a huge impact in chemistry and physics, as well as biology and other things. Okay. One of the things that I'll tell you is that his theory was restricted to a very severe parameter range limitation. I'll talk about that. Okay, and then what we did about 15 years ago was we worked out the theory, the stochastic theory for this, using quantum field theory, and I'll show you that. And then we can create these patterns in a much wider range of circumstances, and we did it experimentally in biofilms with a synthetic biology group. at MIT. So this lecture will be fairly low level, but you know, it should be fun. So okay, so we start off. Here's the picture I want you to think about. In statistical mechanics, we think about particles bouncing around in a box. But then when we try to describe things, we want to use partial differential equations because they're continuous and differentiable, and we know how to do calculus. So we want to look at density. And so in physics, we have physical systems like particles. In ecology, we have organisms floating around in their ecosystem. And then what we might want to know is what is their density in the population. So in other words, what is the population density varying in space of you know, elephants and tigers and things like that, or fish in a marine ecosystem. Okay, so now I'm going to tell you about pattern formation. But this is pattern formation in time, not pattern formation in space. Later, we're going to put pattern formation in space and in time. So let's think about the following thing: a predator-prey ecosystem. So you have a resource, say grass. You have a prey, which is say a sheep. That's a sheep, according to a biophysicist who doesn't know anything about biology. And then you have a wolf, that is the predator. I have no idea what this creature is. Okay? Probably a lynx or something, but I don't know what a lynx is. Okay, so this is the longest running time series in ecology. It goes back 170 years, something like that. So measure the population of hares and lynxes. And the reason you do that is because you want to kill one of these things and sell their fur. And so people who do that kept statistics of the populations. And you can see that they have these oscillations like this. These data aren't particularly brilliant, but there they are. And if you look carefully, it's not maybe that obvious when you look at this by eye. So if you put this through a statistical analysis, there's roughly speaking a phase shift between these things of pi by 2. So what you see here is you see periodic oscillations of the population. You see fluctuations. There's some phase degree of freedom, and one would like to understand where this comes from. And you might think that this is a really simple problem, but it isn't. Okay, so let's just talk about the physics of this. So this is a bedtime story that if you ever have children, you can put your kids to sleep with. So what you do is you say, well, let's start off now. So I've got the prey and the predator, the sheep and the wolf. They have some population. Now then what happens is the sheep eat the grass, so their population grows. Then the predator, the wolf, eats the sheep, so its population grows. Okay, so everything is growing. But now the population of the sheep is going to go down because the wolves are eating all these sheep very vigorously. So their population goes down due to predation. And then the predator, its population goes down because it hasn't got enough sheep to eat. So now the prey, its population starts to go up because there aren't too many wolves around eating the sheep. So then the predator increases again due to increasing prey, and then it carries on and so on and so forth. And if you look at the phase shift, well, the predator can only start to grow after the prey grows, and it has to grow before the prey declines. So that tells you that this phase shift must be about pi by 2. So that's all the physics of this. It's mind-numbingly obvious that this must happen, okay? But it's very, very difficult to see where this comes from mathematically. Okay, now I'll show you why it's difficult. So let's do Ecology 101. So Ecology 101 talks about equations which are sometimes called the Volterra equations or the Lotka-Volterra equations. So we're going to write those things down. So let's have a look at how we would describe it as a differential equation. So we're going to say, well, the prey, their population is going to, they eat the food, and each prey will then make babies, so their population is going to grow exponentially. So du by dt, u is the prey, will grow like b times u, okay? But they can't grow too much because there's only a certain amount of food in the field or whatever. So basically, that's called in ecology the carrying capacity. So basically, the population of u will stop increasing when U is equal to this number. Okay, so it might be 100 sheep can be supported on this in this field, so you can't really have more than 100 sheep. If you do, then the population will reduce. So that's that. But now we've got to deal with the predator. So the wolf eats the prey, and it eats the prey. So the prey population will go down by an amount proportional to how many prey there are, and by an amount proportional to how many predators there are. So there's going to be a term P. How does the predator grow? Well, its population grows in the following way. We'll call predator V. Okay. Well, of course, it grows by food it eats. The food it eats is the prey. So we know it's the same term over here. Predation rate times the prey population times the population of the predator. Each predator eats the prey that it manages to hunt, and then it makes babies and reproduces. But then, of course, they can also die. So there'll be some death rate. The sheep the wolves just die due to, just getting old. Okay. So those are these two equations, and these are called the Lotka-Volterra equations. So now you say, okay, this everything that we told you in the bedtime story that numbs your kids and makes them go to sleep because it's repetitive and it's very boring. Everything is in these differential equations. So you solve them numerically, and this is what you get. So the green is the prey, the red is the predator, and the population density goes to a constant. It doesn't oscillate. The whole story, which we thought the physics of it was encoded in these differential equations, doesn't work. So this does predict a phase shift of pi by 2, but there's no oscillations. There's no periodic, there's no population cycles. Okay. So then you say, okay, fine. Well, let's go and simulate this thing in a computer. So here's my deterministic equations again. And they represent growth, competition for the resource, and predation. Okay, so that's the equation I just showed you. So now let's make a computer simulation. So since we do computer simulations, I want to do a simulation, not solve these equations numerically. I already showed you how to solve the equations numerically. So we're going to do a simulation. How does a statistical mechanism do a simulation? You put a bunch of sheep and wolves in the ecosystem, and then you say, well, with some probability B per unit time, the prey will reproduce and make babies. So this term here, this birth term, stochastically will be represented by this. Then I can say, well, they compete for food. Okay? The grass can only support 100 sheep. That means that they're competing for the food. So that means that they compete and only one of them wins. So that stochastically will be x plus x goes to x. Then there is predation. So the predation term says the sheep beats the predator, and then with some probability p, the sheep gets eaten. So they've gone away, and then the predator uses the energy that it made from the sheep to make a baby predator. So x plus y goes to 2y. And then lastly, the predators can die, so the y can just go into the vacuum state. So that's a stochastic simulation. So I can solve that exactly on a computer. I can use Gillespie's algorithm and simulate it. If I do that, then this is what I get. So here, this line, this purple and this green, those were the solutions of the deterministic equation I showed you before. Here in these colors, whatever they are, you can see that now I have noisy, persistent cycles. So the stochastic model does exactly what the bedtime story said. It said that the system will produce cycles, they'll be noisy in some way, and this will go on forever. And you will have predator and prey coexistence, and they'll coexist in these cycles with roughly a pi by 2 phase shift. So the same physics, encoded by a differential equation, encoded by stochastically, gives you completely different answers. Okay, that's terrible. Okay, that's not supposed to happen. Okay, okay. The previous class that was in here, some of you were here when Professor Intrigator was erasing the blackboard. He was giving in his last lectures, he's talking about things in quantum mechanics called anomalies. So there's a thing called the chiral anomaly, actual anomaly, the trace anomaly, all of these things. Some of you may have heard of these things in COCO and things like this. This is an example. This is a stochastic version of what you have in quantum mechanics as anomalies. The behavior of this system is very different, whether it is stochastic or classical. Okay. So stochasticity recapitulates the population cycles without needing to invoke additional levels of realism, which I'm going to talk about. Persistent oscillations are not reproduced by the deterministic mean field theory without additional assumptions. So the ecologists didn't do stochastic simulations. They didn't try to develop stochastic theory because it's not what they do. So what they did, I will tell you next time.
Would you see the same thing happen if you took the differential equations and added like a noise term, like a Longovid equation?
No.
No. Okay, so it has to be like a Gillespie simulation type.
Yep.
I see.
So in the theory that I'll tell you about, you can derive, you can write down the stochastic theory, you can write it down as a path integral, you can derive the deterministic mean field theory from the path integral, and it looks exactly like the one that the ecologist guessed. And then the stochastic theory, the effective Langevin equation that you could get out from it, you can derive that by doing the loop expansion in the field theory. And the noise is multiplicative noise, not additive noise.
Ah. See.
And the reason is this. There's an absorbing state in this. Let's suppose the wolves eat all the sheep. Okay?
Then,
They're gone. The sheep are gone. The wolves have got nothing to eat, so they're gone. And you've just got the vacuum state, and then after that, nothing happens. So there's an absorbing state which you cannot get out of. If you had noise, then there'd just be some fluctuation, and out comes a sheep. Okay? That doesn't happen, right? And then there was sheep, yes. So no, it doesn't happen. Okay, so next time I'll talk about this.
You don't get like the quantum foam, like sheep wolves pairs.
Well, it is.
creating
Well, you
out of-
do. You do.
Oh yeah.
I'll talk about it. Any questions online? Lingwan, you're online, right? You saw that? Lingwan, are you still there? Do you have any questions?
Oh, yes. No, I don't think I have any questions. I just,
Yep,
I was
no
just
problem.
talking. Yeah.
Yep.
Thank you.
Okay. All right then. See you on Wednesday.
Bye.
Okay. Has everybody here filled out the course evaluation? Okay, I know some of you did it in the class, so everybody's done it. Okay. So I'm going to do 100% response. That'll be great. All right. So let me stop.